Well, good morning, pre-calculus. We're gonna jump right in. We're gonna start off with a do now. It's an entry task. You can follow along. Piece of scratch paper. Put it in your notebook. Do it in your head. Um, I'll draw it on the screen here. So I got an airplane again. Yay! Um, so I don't have a video of an airplane. I don't have a picture of an airplane. I don't even have a bad drawing of an airplane. All I have is the word airplane. So an airplane's velocity can be represented by the vector a for airplane, -2, 9. There's wind blowing. Wind can be represented by the vector w, 2, -1. Our job is to graph a plus w using either tip to tail or parallelogram methods. I'm going to use tip to tail. You can do whatever you want. Um, graph the resultant next, and finally find the component form of the resultant. Okay, well, I'm going to start with vector a. So from 0, 0, -2, 9. It's right there. I will change that to green and just drop an A right there next to it. That's a giant A. Green A. Awesome. All right, and then we're going to graph the wind. I'm going to go tip to tail. So from the end of this vector to -1. So that lines up right there on my coordinate. And it'll be blue for wind. And then let's try dropping a smaller W. That was a giant A. Okay. I got a little W right here for the wind. And then we're going to do the resultant. So the resultant is going to go back to where the pigeon starts at home, right? Using that metaphor, starting at 0, 0 and going to where we just finished drawing that wind vector. All right, well, I'm just going to make this in red. That's the resultant. Find the component form of the resultant. Well, it doesn't really look that hard, huh? So component form, I need my pointy brackets. I got a comma, and then let's see. Didn't go sideways at all. Straight up the runway, so to speak. And so 0, and it goes up by 8 spaces. Yay! Cool. Nice job. So today we're going to look at resolving vectors into components. I don't know what resolving means, huh? Well, by the end of today, you will be able to resolve a vector into component form. So we know what component form is. This resolving business, well, that's what we'll have to learn. All right, quick pop quiz. You got your paper? You write down your answers on a piece of paper. I will give you the address of the school and you can mail it in to me. Just kidding. A vector has blank and blank. These are the things we just got to know. So that's why it's a pop quiz. A vector has blank and blank. You go ahead and say it. Okay. Well, your classmates anyway said something here. So direction and magnitude. Thanks, classmates. Well, oh my gosh. Maybe your classmates can help me draw an E. Wow. All right. So what would happen if we had a vector and it had direction and it had magnitude? So the question is, how can we find component form of the resultant vector, which is in blue? Blue vector there's got a magnitude of 6 and it has a direction. I measured with a protractor 115 degrees there from the x-axis over here to my blue vector. So I was doing some thinking ahead of time, like what could I do to find the component form? So I know I could draw the components, and I did. I drew the components. So I know I can draw the components. I've got a, on the x-axis, it's going to the left. So it's going to be a negative component for the x, and on the y, it's going up. So then I'm going to have a positive y component. I know if I've drawn those correctly, they should give me a right triangle. The resultant is going to be the hypotenuse. I have no idea how big the components are going to be still. Right? There are a lot of possibilities. If I'm doing a squared plus b squared equals c squared, it's a lot of possibilities. They're going to work for x and y that would still give me a hypotenuse of 6. I mean, I thought of at least 2. I think probably it's infinite though. Huh. Well, you know what? There actually is, there is absolutely, I mean, you guessed it. That's why the title is resolving vector components. So there is totally a method to find the component form. That's what we're going to learn today. And to get some formulas, you need to write these things down. Took a screenshot out of our textbook. I don't know if any of you guys got your textbooks at the materials pickup earlier this week. Um, you can crack it open. And if not, then here's a screenshot of the textbook. So I highlighted a bunch of stuff. The highlighted stuff is the important parts. There's a whole paragraph of text. I mean, you got a whole textbook. It's got like thousands of pages. There's a lot of words. So in order to find the components of a vector, if we're given the direction and the magnitude, we can use those two pieces of information to calculate the components if we're not given the components to begin with. Okay, and so there's a couple of things, three things that we need. These two formulas, the red one, the green one, plus one more thing that's on the next page. So in order to calculate component form, we need the magnitude. So in the, these are the same formulas up here highlighted, and I just copied them down here so that they're bigger and easier to see. The textbook put the formulas into component forms. So it's like, hey, look, if you're going to find the component form of a vector, this red part, you can see it's in the pointy brackets. That's where the x component would be, and then there's the closing pointy brackets. This green part is where the y component would be. Okay, so we have these two formulas. I'm going to point down here because it's a little bit easier to see stuff. So you need the magnitude of the vector. That's just its length, right? So in the problem from a minute ago, the vector that I drew had a length of 6. And then we're going to do the cosine of the angle. Okay, and it's not just any angle, it's a very particular angle. You can see as a little bit lighter highlighting, but it's a thing called the direction angle, which I will define in just a minute. It's on the next page. Okay, so it's not just any old angle that you happen to find. It has to be the direction angle, which has got a specific definition. Okay, to find the y component, very similar formula. You can take the magnitude, multiply it by the sine of theta. Theta meaning the direction angle. Okay, so just a quick note, make sure your calculator is set into degree mode. When we're calculating these trig ratios, sine and cosine, if you're not in degree mode, it's going to look like your calculator is doing what you're supposed to, but it's going to give you the wrong answer because it's in some other mode. Okay. And to be honest, degrees are pretty dumb. We're going to learn something way better than degrees, but we haven't yet. So make sure you're in degrees for now, and later we'll learn something better than degrees. Okay, so we got our two formulas. Write these into your notebook. And then the other thing we need to know is direction angle. So direction angle has a very specific mathematical trigonometric definition. We always measure direction angle on a graph starting from the positive side of the x-axis, right? Not the negative side, the positive side of the x-axis. That's the right-hand side. And then we always rotate counterclockwise starting from the positive side of the x-axis. Okay, so here's my x-axis. Positive side's over there. So I'm going to start at 0 degrees, and then I'm going to rotate counterclockwise. Right, just like that. Okay, so 0 degrees can be over there, 90 degrees would be straight up. I can't bend my arm this way. 180 degrees can be straight over there. 270 is down, straight down, and then my arm doesn't bend this far either. So 360 degrees, the same place as 0. That's where we started. That'll be the positive side of the x-axis. So here's a little illustration that it gives us some of the more important or more commonly used angles at any rate. So you can see the in green here, the angles I just highlighted, those quadrantal angles are the like every 90 degrees. Okay, so then that goes into your notes. Those three things need to go into your notes. The two formulas to find the x component and the y component, and direction angle. Okay, have to start at the positive side of the x-axis and rotate counterclockwise. Okay, let's jump back to that example I had drawn a few minutes ago and see if we can't find the two components. I'm pretty sure I had x component in red. So I'm going to need the magnitude of the vector, which is 6. I'm going to multiply that by the cosine of this angle, 115 degrees, which we didn't notice this before, but this is measured from the positive side of the x-axis. Right? It's the right-hand side of the graph. and it's going counterclockwise around from the positive side of the x-axis until we get to where that vector's at. Okay, so 115 degrees. And then I'm gonna pull out my calculator and let's see if we can calculate that. Your calculator probably is way nicer than mine. Mine is super clunky and hard to use because it's just the one that shows up in Windows. So I gotta type in the angle first. So I got 115 degrees and oh, see right here, I'm in degree mode. Your calculator probably shows that somewhere else, but I'm in degree mode, so that's good. I'm gonna go to trigonometric functions and I need cosine. Blam, cosine. Probably on your graphing calculator, you hit the cosine first and then the angle, and then you hit enter, and it tells you, it's going to tell you that number. Right, that's a lot of decimal places. Okay, so that is the cosine of 115 degrees. I need to multiply by 6, so times 6 equals blam. All right, let's see if I can copy and paste. That's like a lot of decimal places. I'm just going to go with 2. So really, this would round to a negative 2.54. But let's see if I can copy and paste it. I can. Okay. Paste. Actually should round to 4. Yeah. Okay, cool. And then let's also do the y component. So I'm pretty sure I had that in green on the last page. So this is going to be 6 multiplied by sine of 115 degrees. Okay, so I'm going to grab my calculator again. Clear out that previous answer. So 115 trig sine equals, whoops, nope, should not have hit equals. 115 sine, okay, it's done the sine now, that's the 0.906. Now I still need to multiply by 6 for the magnitude. Now I hit equals, all right, copy. So this is going to round to 5.44 because that's 7 right there. So I'm going to copy it, paste, bring this over to the right. Oh, I missed this thing over here and round. Okay, so that doesn't actually, I don't have a problem with that. That doesn't make sense. We talked about before we even knew how to find component form. I'd said the x component should be negative, right? Because I'm going to the left on the x-axis, and the y component should be positive. I'm going up in the y direction. You know, it's maybe not drawn to scale, but it looks like the y component should be bigger than the x component. That's the way it looks on the graph, and that's what I ended up with. The magnitude of the y component is, like 5, which is like twice as big as the magnitude of the x component. Okay, so altogether, my component form would be negative 2.54 and 5.44 inside of my pointy brackets. Circle the final answer. Normally I like to circle this with something creative, but I don't really have enough space to use a creative pen this time. Maybe on the next one. Okay, hey, let's that's it, right? That's a wrap. I'm gonna do a couple more examples just to make sure that we get this whole thing cleared up here. So here's some practice. I'll do the practice. You can try the practice on your own. I'll wait while you try. So here's 2 vectors. The first one, magnitude of 15, direction angle of 120. The second one, magnitude of 6, and direction angle of negative 50 degrees. Never seen negative numbers on protractors before. What? I'm sure you'll be able to figure it out. Okay, so I'll wait for a couple minutes while you try those out. Fast forward. All right, so you should have hit pause actually. So I'm gonna go ahead and ask you what you got. Oh man, I wish I could. All right, so I did the same 2 formulas. I guess I'll write them down before I show you the answer. That's probably a better idea. So to find the x component, 15 times the cosine of 100 and 120. Cosine of 120 degrees. It didn't write. It's totally what I wanted to do though. Cosine 120 degrees. Oh, beautiful. Okay, and then to find the y component, we'll just go over that in green. I don't erase. It'll take too long. 15 times the sine of 120 degrees. Okay, so my calculator is still set in degree mode, and got the answer hidden right here. Negative 7.5 in the x component. Yeah, that looks like what I see on the graph, and 12.99. Probably round it to 13 from the y component. Nice. All right. Number 2. Practice problem number 2. Okay, so magnitude of 6. Let's see if I can squeeze stuff in here. Multiplied by the cosine of, what did you guys use for the direction angle? Yeah, so there's actually 2 different options. This is pretty interesting. Some of you might have just said, hey, you know what? It says negative 50. I'm going to do the cosine of negative 50. And others of you might have said, you know what? I actually was paying attention when Mr. J was talking a minute ago, and direction angle is always measured in the counterclockwise direction. And that means I should go the other direction around this circle, right? If I start at the positive side of the x-axis and go around this direction with my protractor, well, the whole circle would be 360, and this part is like negative 50, so 360 minus 50 should be 310, right? You could use 310. I'll put that right here. So here's 2 different versions. 6 times, man, I wish you could read that. What did I just wrote it and I can't even read that. Okay, it says cos is 6 times cosine of 310 degrees, right? I can say things better than I can write them. 6, that's better, times cosine of 310 degrees. Okay. And here's the secret. They both work. You can do either one. You can use the positive 310 degrees, that is technically the direction angle, but you could also use the negative 50 degrees. And either way, you're going to get positive 3.8 for your x component, right? Okay, so the thing is, when we assign direction angle to be positive in the counterclockwise direction, then that means, you know what, as long as you start at the positive side of the x-axis, if you go counterclockwise, we'll call that a positive angle. And if you go in the clockwise direction from the positive side of the x-axis, went down, that would be a negative angle. And your calculator will handle either one. So the same thing would hold true for the y component. I guess there's room down here if I write small. So the magnitude is still 6. And now I do the sine of either negative 50 degrees or 310 degrees. Does not matter. Wow, that is so neat. If I actually take my time and write slowly, you can read it. I don't know if I can fit negative 50 in there with parentheses. Wow, I did it. Okay, I'm so impressed with myself. Wow, cool. Okay, so either way, positive 310 degrees or negative 50 degrees, either one is going to give you the same answer. 6 multiplied by the sine of 310, negative 4.6. Again, we can see on the graph that the y component should be negative. It's going down. Awesome. Well, there you have it.